Hello everyone and welcome to another part of the Galaga SDL tutorial videos, and in this video and the following one we're going to be finalizing our collision detection system. So in this video we're going to start using our collider arrays instead of a broad face collider, and we're going to also implement our circle box collision detection, and then in the next video we're going to be implementing our box-box collision using separating axis theorem. So for this video we can start at the physEntity class. In our check collision we're going to stop using our broad face collider as our only colliders. So we're going to create a boolean and we'll call this one narrow face collision or narrow face check, which is going to start off being false. Now we're going to check if both entities have a broad face collider. So we're going to say if M broad face collider and other M broad face collider, we want to do the broad face collision check that we have here. So we can say narrow face check is going to be equal to what we had there. Because if this fails, there's no point in checking the narrow face collision. And if one of the entities don't have a broad face collider, we need to do the narrow face check anyway. So we can say else narrow face check is going to be equal to true. So if we do have broad face colliders, use them and check. If not, do the narrow face check. Now for this return, we can just say return false, because if all this fails, we just want to say that the collision check is false. Now for our narrow face check, we can say if narrow face check, we need to loop through both collider arrays and check them against each other. So we can say for int I equals 0, I is less than m colliders dot size I plus plus, for nj equals 0, j is less than other m colliders dot size j plus plus. So we just loop through both our collider and the other colliders, and then we can say if collider check between m colliders at I and the other m colliders at j return true, because all we need to check for is for one of the colliders to collide with the other one. We don't need to keep checking all the other colliders. And that will be it for us using our narrow face collision. Now of course all our colliders are boxes for our narrow face collision, and we don't have a box-box collision check. So for this video, we're going to start with our circle box collision, and then the next one, we are going to do our box-box collision check. So to do our circle box collision check, we need to go to our phys helper or physics helper .h. So physics helper .h, and we need to add another if here for our box and circle collision. So we can say else if C1 get type is equal to a box and C2 get type is equal to a circle. So if C1 is a box and C2 is a circle, what we want to do is to do a box circle collision. So let's create the function here. Just like the circle collision, we can say inline boolean box circle collision box collider pointer, which will be our box, and a circle collider pointer, which will be our circle. And then what we want to do is pass these colliders into this function. So we can return box circle collision of a static cast. So static cast into a box collider pointer, which is C1, since our C1 is our box, and the other one will be a static cast into a circle collider pointer, which will be our C2. And that covers the case where C1 is the box and C2 is the circle. So what if it's the other way around? All we need to do is pretty much just replace these two or flip them. So we can just copy and paste this one And now we can say if C2 is the box and C1 is the circle, we want C2 to be passed in as the box and C1 to be passed in as the circle. And that will be it for our if statements right here. Now for our box circle collision function, what we want to do is to pretty much figure out how we can do box circle collision checks. Now there are two cases where a box and a circle can collide. The first one will be, so let's say we have our box here and we have a circle that we need to check if it collided with the box or not. Now the first case will be if the circle lies on one of the edges of the box. And to do that, so that circle will always, for it to collide, it will always have to lie on one of these edges. Now the second case where it doesn't touch any of the edges is if the circle is completely inside the box. So we need to handle these two cases. And the first one we're going to handle is if the circle is lying on one of the edges. So how would we figure this one out? To do this, what we're going to do is say that we need to find the distance from the center of our circle, so this point here, to the edge that we're checking. So let's say if we're checking the 2, 3 edge right here, we need to find the distance from the center of the circle to this edge, the closest distance. And if the closest distance is less than the radius of the circle, it means that the circle lies on that edge. If it's more than that, so if the closest distance to, let's say, this line here, which would be the start point of this line, so it would be all the way down here, it's more than the radius, that means it doesn't lie on this edge. And that's pretty much what we're implementing. We want a way to find the distance of a point to a line segment. And to do that, we're going to implement a function that does this for us. And this function will be called, so we'll do inline float point to line distance. And what this function is doing is pretty much what its name says. So we have a const vector2 reference, which will be our line start, a const vector2 reference, which will be our line end, and finally a const vector2 reference, which will be our point. And that will be it for the parameters that we need. Now inside here, what we want to figure out is, so how will we exactly figure out what the closest distance is? And the idea here is that we need to figure out a vector that's starting, let's say this is the start of our line and this is the end. We want the vector to be along this line, which is pretty much the slope of the line. And to get this vector, we need to subtract the end from the start of the line. So let's do a vector2 slope, which is going to be equal to line end minus line start. And then what we want to do is to project the point from, let's say, this point right here to the start of the line. We need to project this onto the slope. And this will make sense in a little bit. So let's do that, but the problem is to do projection, we need to do the dot product of a vector. And we don't actually have a function to do this for us yet in our framework. So let's implement that. We will go to our mathhelper.h. So mathhelper.h. And then we'll scroll all the way down to our rotate vector and then add a couple of functions in here that we need. The first one will be our dot product. So we'll do inline float dot, and this one will take a const vector2 reference of vec1 and a const vector2 pointer or reference called vec2. And then we're going to be returning vec1.x. So vec1.x multiplied by vec2.x plus vec1.y multiplied by vec2.y. And that's pretty much it for the dot product. We also need another function, which is a clamp function, just so that we can clamp our value between 1 and 0. So for our clamp function, we can do inline float clamp And what this will take is a const float reference, which will be called value, a const float reference, which will be called min, and a const float reference, which will be called max. So the idea here is if the value is more than the maximum, we need the value to be equal to the maximum. If it's less than the minimum, it needs to be equal to the minimum. Otherwise, we just return the value back. So we can say if value is more than max, return max. If value is less than min, return min, and then return value at the end. And that's pretty much the two functions that we need inside our math helper for now. So now that we have them, we can go back to our phys entity, or physics helper, I mean. And now we need to do a pretty complicated line, but I will explain what it's doing piece by piece, I guess, because it is using a few functions. So what we're doing is a float param is going to be equal to clamp the dot product of point minus start, or line start, and the slope, and then we're going to be dividing this by our slope dot magnitude square. And then for our clamp, it's going to be 0.0f and 1.0f for the minimum and the maximum. Okay, so let's see here what is going on. We have our dot of our this minus that, there we go. So the dot of point minus start line, comma, slope. So we're getting the dot between the point to the start line, which should be, so the point to the start line, this vector right here, we're projecting it onto the slope of our line, which is a vector pretty much from the start to the end of the line. And then we are dividing by the magnitude because we want to eliminate the magnitude of this slope here. What we want to do is to only get the projection of this vector onto this one, of the length of this vector. And that's pretty much what the division by the slope magnitude square is. And then the clamp is so that if the projected vector lies after the start right here, or before the start, I guess, it would be equal to the start. And if it lies after the end, it would be equal to the end. Because what we're trying to do here is that we're trying to make it a line segment, not just a straight line. So if the point is way too far, that means the closest point to it is this point right here, the furthest point on the line that is closest to that point. So that's the idea here, and why we're doing the clamp of the value, and then that's why we're doing the projection. Now, finally, we can get our nearest point. So vector 2, nearest point, is going to be equal to line start plus the slope multiplied by the parameter. And the idea here is that we are projecting on this line because what we're doing is we're pretty much getting this vector from the point to the start, projecting it onto here. Now we have a distance from here to here. So we know how far along the slope we moved. So what we can do is start from the start of the line here, move along the slope for that distance up to the parameter, and then stop right there, and that would be the point closest to the line. And that's pretty much it. It's I know it looks pretty complicated because it is using a bit of linear algebra, but once you get the hang of it, it makes a lot of sense, and it makes it a lot easier to find a point on a line segment, or the nearest point of another point on a line segment. But what our function wants to return is the distance. So we can say return the point minus the nearest point dot magnitude. So we want this distance right here. the distance from the closest point to our point. And that's pretty much it for that function. And that's pretty much all we need to figure out if the circle lies on an edge. So now we can use this function to do our collision check. So we can say if point to line distance, but now we need to find the vertex position of our collider. We right now don't have a way to find these positions easily. To do that, we need to go to our box collider.h. So let's go back to our box collider.h and let's add a new function. So this function, we already know where our verts are because they are stored in this array, but they're game entities. But we're only concerned with the position. So we can do a vector2 function called get vertex position. So get vertex pos, and that will take an int index. And then let's implement this function. So in our box collider.cpp, what we want to do is to say return mverts at the index that we passed in position. Of course, this is by default in the world, and that's what we want, so that's fine. So we're returning the position of the vertex of the given index, and that will be it. So now we can go back to our phys entity or physics helper.h. And so what we're doing is point to line distance of, so our first line will be 0 to 1. So we want index 0 to index 1. So we'll say box get vertex position at 0 and box get vertex position at 1. Now the point that we're looking for is the center of our circle, which is its position. So we'll say circle position. And of course this is still in world space, so that's fine. So now we supplied it with all three parameters: the start line, which is our vertex position at 0, our end line, which is our vertex position at 1, and our point, which is the middle of our circle. Now we need to compare this to something. So as long as this value that's returned is less than the radius of our circle, so circle get radius, that means a collision happened. But since we're only checking this line, we also need to do the same thing for this line, and that line. And the reason I have it 0, 1, 2, and 3 is because this is the way we have it set up in our box collider. So our box collider is negative on the x and negative on the y, which is this one here. And then, let me move that to the side, positive on the x, negative on the y, which is here. Negative on the x, positive on the y, which is this one here. So that's 2, and then that's 3 right there at the end. So I hope that everything is clear so far. Now we can go back to our physics helper.h and implement the rest of the lines. So we can do or, and then copy all of this and paste it a few more times. And then let's do this. So we don't need the last or here. Okay, so now we have 0 and 1, this one. We need to also do 0 and 2. So we'll replace this one here with 2. We'll also need 2 and 3. So we'll do 2 and 3. And finally 3 and 1. So the last one will be 3 and 1. And that will be it for these checks. So if any of these succeed, that means the circle is on one of these edges, which means that we want to return true. Otherwise, we want to return false. And that will pretty much be it for our edge case. So let's now test it out. And to test it, we don't actually have a narrow phase collider that is a circle. So we can go to our butterfly.cpp and we can go down to the constructor over here. We can, instead of doing add a collider, we can just comment this out and paste it right underneath here. And we can add a circle collider instead. So this is a circle collider, but we haven't added this to this file. So all the way at the top, we can include circle collider.h. and then let's scroll back down to where it was, and this only takes a single value, which would be, so right now we're passing it a vector, so we can just do .x, so scale dimensions.x, and that will be it for setting a circle collider to our butterfly to test out our new setup. So let's try to run it and see what happens. Oh, we're getting an error here, so let's see what's going on. Right, so forgot the brackets here for size. Let's see now what happens. And there we go. So now that our butterfly doesn't have a broad face collider, it should not have a blue collider, it should only have a red one. And there we go. So it only has its red circle collider. So let's wait for it to, for all the enemies to get into formation, and then we can check when a butterfly dives and see if we can actually collide with it. So what we're looking for is for the circle collider here to collide with one of the small boxes of the player, not the broad face collider. There we go. And one of the butterflies started coming down. There we go. And as you can see, it hit the box here. It didn't trigger as long as it was hitting the outside circle, but as soon as it hit the inner box, that's when the collision detection happened. And that seems to be working pretty well. Okay, now for the second case, which is if the circle is completely inside the box. And to give you an extreme example why this needs to be done is, let's say our circle collider has a radius of 0.0f. It's just a single dot. What would happen now if we try to check for circle box collision? In theory, since a distance of 0 doesn't really happen at all, what's going to happen is that the butterfly is just going to fly right through the player, and no collision detection is going to be triggered. There we go. So as you can see, there is no collider here since our radius is 0. So it should be just a single dot in the middle of the entity. There we go. So that's flying down now. And as you can see, you can just fly right through the butterfly and nothing happens. So let's implement our second case. So let's go to our physics helper.h. And for this one, we are going to do a point in polygon function. So let's go to the top here and do inline boolean point in polygon. And this one will take a vector2 pointer, which is verts. So this one will be an array of vertices that we want. And then int vert count. Of course, since this is a polygon function, we can pass it a box, but later on we can have a pentagon or whatever kind of polygon that we want to pass in. This function also works for concave shapes, which is really nice. And then const vector2 reference of the point, which is the point that we need to check. Okay, so to explain a little bit what this function needs to do, let me open up this thing right here. So paint here. Let's say we have a point inside the polygon. What we want to do is project a line to the right. And if the number of lines that we crossed is odd, that means that point was inside the polygon. If it's even, that means the point was outside the polygon. So if the point is here outside, it needs to cross 2 lines, whereas if it's inside, it needs to only cross 1 line. And you'll find that this is true no matter what the shape of the polygon is and where the point is, or whatever the line is that we project. Actually, if we project this way, it only crosses 1, 2 lines, and that's it. But it's much easier to send the line off to the right side, and that's it. The polygon that it needs to check against, it doesn't have to be oriented a certain way. It can be oriented in any different way, and it should work properly. Okay, so let's first start off by creating a boolean. We can call this one red val, so the return value, which is going to be equal to false. Now we need to loop through all the vertices of our polygon. So we can say for int I equals 0, j, or this is a comma by the way, so I is starting off at 0, j is going to start off at vertex count -1, and then I is less than vertex count, and then j is going to be equal to I plus plus. There we go. And let me explain for a second what this statement is doing. So I is going to start off at 0, and let me go back to our square here. So this was 3. So I starting off at 0, j is starting off at vertex count -1, which is at 3. So this is our I here, this is our j. And then our I is going to be plus plus, which means that our I is going to go to 1. But before that happens, we're assigning the old I into j. So j becomes 0 and I becomes 1. And then after that, j becomes 1 and I becomes 2, and so on, right? You'll notice that we have 0, 1, 2, and 3. So to loop this way, we need to create an array in a way where we have 0, 1, 3, then 2 inside the array. We can't have 0, 1, 2, and 3 because of the way that we have our boxes set up. So let's get started. We can say if verts at I dot y is more than or equal to point dot y is not equal to verts at j dot y is more than or equal to points or point dot y. Let me put a bracket here, and there we go. And let me explain what this if statement is doing now. So we're saying if the vertex at I dot y is more than the point dot y, so let's say our point is right here, and we're checking for this line here, right? So if we have our 0 dot y, if it is more than the point, which is not true, that's going to be false, is not equal to j dot y, which is for the one is over here, is more than the point. So we want at least one of them to be above the point and at least one of them below the point. Because if they're both above the point or they're both below the point, we know for sure that this point, if we go to the right, we will never cross that line. And that's why we have this if statement here, so that if any line segment is above or below the point, we don't need to check it. We only are concerned about line segments that have their y on one point above the point and their y on one point below the point, because we know for sure we might be able to cross it. I hope that makes sense. Now, to move on to a bit more linear algebra. So we'll do a vector 2, call this one vec1, which is going to be equal to bracket verts at I minus verts at j dot normalized. And I hope that makes sense by now. We are going from I, which is 0. By the way, since we're setting up our array in a different way than what we have it set up in the box, technically this one will be, so this one over here will be our 3, and this one will be our 2. And that's the way we're going to set it up a bit later. So we have our 0 and 3 right here. So we're getting a vector from I from 3 to 1, and we're normalizing it to get only a unit vector. That's pretty much all what this is doing. So we want to create another vector 2. We'll call this one PROJ. So projection is going to be equal to verts at j plus vec1 multiplied by the dot product of the point minus verts at j and vec1. Okay, So let me explain what this is doing here. So we're starting off at vertex at J, which is our 3 right here. And we're projecting from the point to J, right? So we're starting from the point here to J, or from J to the point, since we're subtracting from the point. So we have our vector right here. Now we have this line right here as well, right? So we're projecting this along our first vector that we got, which is the unit vector here. So our projection is going to look something like this. So it's going to be this line over here. So moving along this edge, this line over here, this is going to be our projection vector. And then we're moving it back to our vertex J so that we can have this point right here. And then finally, we can say if the projected point dot x is more than our point dot x, red val is going to be equal to not red val. And then finally, we can just return red val. Okay, so what we're saying pretty much is we're projecting down this point, and if this point dot x is more than our point, that means we're gonna cross it. Because remember, we are sending a line off to the right. So since this dot x is less than our point, that means we're never gonna cross this line, and we don't need to worry about it. And then since these 2 points are above our point and these 2 points are below our point, we can ignore these 2 as well. So these 3 are not going to happen. And then for this one, it's dot x, which is going to be, so we're going to start off at 2. We're going to project down to our point. We're going to have our projected line right here. So our dot x is going to be somewhere over here. So our dot x is going to be more than our point, which means we are going to go through it. So we are flipping our red val. So red val is returning as going to be false to begin with. We cross one line, it's going to be true. We cross 2 lines, it's going to be false, which means we're outside. We cross 3 lines, it's going to be true again, and so on. Because if it's odd, it means we want it to be true. If it's even, we want it to be false. And that's pretty much it for point in polygon. Now we can implement that into our collision detection. So we can go down here in our box circle collision, and let's create our vector array that I was talking about earlier. Because we have, right now we have 0, 1, 2, and 3 for our box collider. We want to turn that into 0, 1, 3, and 2. So let's do a vector 2 quad, which is going to be of size 4. So we can say quad at 0 is going to be equal to box get position, get vertex position at 0. And then we can copy and paste that. So for all 4, this one is 1, this one is 2, this one is 3. So this is going to be 0, 1, 3, and 2. So all we did is we had 0, 1, 2, and 3. We flipped the 3 and 2 so that it works properly in our setup up here. And then we just need to pass in this array into our function along with the position of our circle, and that should work. So we can say if polygon or point in polygon quad, of course the size of the quad is 4, and circle position. So if this function returns true, we want to return true as well. Otherwise, we want to return false all the way at the end. So let's run this and see if it works. There we go. Of course, our butterflies still have a radius of 0, so we can see their colliders. But technically, if everything worked correctly, we should still be able to collide with the butterfly, even if our circle collider has a radius of 0. So let's wait for it to get into formation, and then we'll test it out, and hopefully it works. There we go. And there we go. That seems to work. And now that's pretty much it for our box circle collision. And that pretty much wraps it up for the video. I really hope that it helped. Next video, of course, we're going to do the box-box collision. If you have any questions, suggestions, or feedback, please leave them below. Otherwise, thank you very much for watching, and I will see you in the next video.